Hello, this is Jack Jackson, and we're back again talking about inferential statistics. In this video, we're going to talk about confidence intervals. And actually, they're going to have a series of videos here introducing confidence intervals. So this will be broken up into several videos. Right now, the plan is to do about 7 of them here, with each one of these little topics representing one of the videos. And in this one here is going to be about just introducing the idea of confidence intervals and getting us set up so that we can create one. Really, you're going to need at least the first couple of these before we can get to where we can actually make a confidence interval. So this is going to be broken up together. Together they will introduce this. So we're looking at 4.3.1 confidence interval introduction. So if you remember from our last video, we were saying that we could use a point estimator, for example, the sample mean, as a single number to estimate, say, some corresponding parameter, like in this case the population mean. But it's a single number, and that single number is going to vary from sample to sample. It's almost certain that the point estimator is at least going to be slightly different, if not a lot different, from the population parameter. And we don't have any measure of how confident we are that the point estimator is close to the actual target parameter, or any kind of measure of how close it might be. And again, it's like trying to hit a target that's just a little dot with the tip of a dart. We're probably always going to miss, hopefully not by much, but probably by a little bit. So the idea behind a confidence interval is what's going to be the solution to this problem with point estimators. So instead of just giving a single number, the point estimator, say the x bar value, to estimate a population parameter, what we give instead is an interval of values centered on the point estimator to approximate the population parameter. And this interval is called a confidence interval. So in other words, or for example, what we want to do is estimate, for example, the population mean, mu. We want to use a confidence interval to form x bar minus e up to x bar plus e, and the e is called the margin of error. Notice that x bar is exactly right in the middle of that interval. So we've taken our single dot, the sort of the tip of our dart, and we've sort of given it wings. We've stretched it out on wings of width epsilon on both sides, and we're able to hopefully somewhere between x bar minus e and x bar plus e, we hope that the true mean mu is actually in that interval. Okay, and so that we hope that will happen. Furthermore, we can use our knowledge of sampling distributions to assign a level of confidence to this interval. So we might be, for example, 90% sure that our interval includes the true unknown value of mean, of the mean mu. So we're working towards developing an interval like this. So in this particular lecture, we're going to focus specifically on constructing a confidence interval for the population mean of the form x bar minus e to x bar plus e. Now the techniques we're going to use are going to use a couple of assumptions. Assumption number 1 is the distribution of sample means is normal. Now, if the population is distributed normally, then this assumption number 1 is definitely true. If the population mean is not distributed normally, then this assumption is not true, but it can be approximately true if the sample size is large enough. So this is where the central limit theorem that we studied earlier comes in. By the central limit theorem, if the sample size is at least 30, for any distribution we have, then this distribution of sample means is distributed at least approximately normal. And this assumption 1 is also true for smaller n's than 30 if we know the underlying distribution is somewhat close to normal. And of course, it's exactly true if the underlying distribution of individuals is exactly normal. So assumption number 1 in many cases is actually a good assumption. Okay. Assumption number 2 is that we know sigma sub x, in other words, the standard deviation of the population of individual measurements. Now, this is actually not usually a good assumption. The whole point here is we don't know the population mean, and we're trying to estimate it. Well, it's kind of unlikely in a real-world setting that if we don't know the population mean, it's probably not likely we're going to know the population standard deviation either. But it's better for developing the results that we have here if we do make this assumption. And then we're going to see in a little bit later on down the line what we can do to use, what do we do if the sigma of the x is unknown, if the standard deviation is unknown for the population. We'll actually change it from what we call a z interval to a t interval, which is kind of just a variation on a theme here. So we're going to look at an example here, and we're actually going to use this example over the course of a few of these little videos as we develop the idea of a confidence interval, at least over this video and the next one for sure. So suppose that we're interested in knowing the mean weight of all 7th grade boys in the United States. Now think about it. It's impossible to measure all of these boys and find their weights. So what we're going to do is we're going to take a sample and measure their weight. So suppose we take a random sample of 36 boys that are 7th graders in the United States, and we find the mean weight of all the ones in our sample. And let's just suppose for argument that x bar is exactly 100 pounds. And all of the data that I show here about this example is going to be made up data. So let's just pretend this is true. Now we know that the best point estimator of the mean weight of all 7th grade boys in the U.S. is this sample mean of 100 pounds. So if you had to ask me at this point, what's the average weight of all boys in the United States, 7th graders? I would say, well, it's probably pretty close to 100 pounds. Now, furthermore, suppose we know from history, for some historical data, that the standard deviation in weights of all 7th grade boys in the United States is sigma, which equals 12 pounds. Again, that's probably an unrealistic assumption, but let's make it anyway. And we're going to be using this example in the following several slides, and this video and the next one at least, to help us develop concepts and formulas for confidence interval approximation of the mean in this case. So the point is we're looking for the mean of the population. Mu, we don't know what it is. We think it's probably close to 100. So we have a point estimate already. Now suppose we went and took another sample of a different 36 boys, found those weights. Well, we would expect we could compute the mean for that, and we would not expect it to be exactly the same as 100. It might be a little more, it might be a little less. We would think it was probably going to be pretty close from sample to sample, but not necessarily the same thing. So it might be, but both the mean of the first and second sample may be slightly different from the true mean of the population. So if we repeat this sampling procedure over and over again, these sample means have a distribution of their own. Okay, here are a couple of questions based on our earlier work you should be able to ask, or I'll ask, and you should be able to answer them. What type of distribution does this set of sample means have? What is its mean? And what is its standard deviation? Okay, you should be able to answer that. So let me ask you to press pause here, think about this one, figure out an answer, and then come back. Press pause now. Well, what type of distribution does it have? Since n equals 36, which is greater than 30, the distribution of sample means is approximately normal, and that doesn't require us to know anything about the distribution of individuals. As it turns out, it's probably likely correct to assume that the distribution of individual weights is probably also normal, or at least close to it. So we probably could have even been okay with this had n been less than 30. But here, certainly n is greater than 30. We're pretty confident that the distribution of sample means can be approximated quite well by a normal distribution. What's the mean of this distribution? Well, the mean of the distribution of sample means is the same as the unknown mean of the population of individuals. So the mu of the x bars is the same as the mu of x's. We don't know what it is. That's part of the whole point of the exercise, is to try to figure out some estimate for what mu is. What's the standard deviation of the distribution of sample means? Well, remember that the standard deviation of the distribution of sample means is smaller than the distribution of than the standard deviation of the distribution of individual values. Specifically, the sigma of the x bars is the sigma of the x's divided by square root of n. In this case, that's 12 was given to be sigma of x. N is 36. Square root of 36 is 6. 12 divided by 6 is 2. So sigma of x bars is 2. So when we're dealing with computations related to the sample means, the standard deviation we're using is 2, and the mean is, well, it's unknown. So a z-interval example, when we're talking about the distribution of sample means, let's see. Suppose we also know that the distribution of individual weights is exactly normal. Then we know that the distribution of sample means is exactly normal. And suppose that, unknown to the people doing the sample, that the actual mean of the population is mu equals 101 pounds, and the individual weights are distributed normally. Now remember, sigma, or sigma of the individual x's, is 12. Sigma for the x bars was 2. Draw graphs of the probability distribution functions, PDFs, for the distribution of the individual weights and the sample means of samples of size n equal 36 using the same axes. So you should be able to do this on your calculator. Go ahead and do this now. This is using skills we've learned earlier. Press pause. Well, now that you're back, we can check this. And remember, x is normal with mean 101, standard deviation 12. X bar is normal with mean 101, standard deviation 2. So I can graph that by, these of course both be normal curves, bell-shaped curves. I could graph that by doing y1 equals normal PDF, x, comma, 101, comma, 12. And then y2 be normal PDF, x, comma, 101, comma, 2. And so these will graph the bell-shaped curves. It turns out what I used here was x-min going from 60 to x-max of 140, marking off in tens. And the y-scale, I went from negative 0.02 to 0.2, and going by 0.1s. And this is the graph that I got with that window. So the shorter, fatter one is the distribution of individuals. That's the one with standard deviation of 12. And the one with the standard deviation for 2 is much more tightly packed, much more of the density near the mean, and so it's humped up higher and closer here to the mean with less as you go out to the sides. So in this case, though, the mean of both of them is 101, so that's centered up. Here's the same picture that I used Minitab to draw the graph of it. So the distribution of individuals is the red graph, the shorter, fatter one. And the black graph is the distribution of means, sample means, x bar. Okay. And let me go back. So look at that again. Notice that the distribution of sample means has the same center, 101, but a smaller standard deviation. More of the data is near the mean, less variability. So now I'm going to basically erase the red graph and kind of zoom in the scale, or zoom out. Yeah, zoom in actually horizontally here. Leave the top about where it is, and spread this so this will look more spread out. I'm just going to regraph the black graph only. And when I do that, I get this graph right here, which is the graph of the PDF for the sample means, the distribution of the x values. Okay, so a nice little bell-shaped curve. So what our task is we want to find an interval so that we're reasonably sure our interval will contain the true mean. So what we begin by is establishing what we call a level of confidence, and we label that 1 minus alpha. So that's the probability that the interval will contain the true mean. And so then alpha then is the probability that the interval does not contain the mean or misses the mean. So that means we captured our mean with our little dart with the wings. That probability of that happening is 1 minus alpha. Probably we missed it altogether, including even the wings on our dart missing. That's a probability of alpha. Now, these 1 minus alpha and alpha are probability values. They can be anything between 0 and 1. But the usual suspects, the usual values we use for confidence level are typically 90%, 95%, and 99%. But it could be anything. We could talk about a 92% confidence interval or an 87% confidence interval. But it's usually a 90, 95, or 99%. And of course the corresponding alphas are 10%, 5%, and 1% respectively. So let's go forward here for a minute, and let's assume that we want to be 95% confident that our interval is going to contain the true mean mu. So 1 minus alpha is 95%, or 0.95. So over the next several steps, we're going to see how to develop and derive a confidence interval. So we want to start by finding an interval that's centered on and symmetric about the actual mean that corresponds to a probability of 95%, the red shaded area under the curve. This interval is not the confidence interval, but will end up having the same width as the confidence interval. So basically we got our little normal curve that, unknown to the researchers, has a mean of 101 and a standard deviation of 2, and we want this red area between mu minus epsilon to mu plus epsilon to have an area of, under the curve, of 0.95. In other words, the probability that x bar is between mu minus e to mu plus e is got to be 0.95%, or 95%, which is 0.95. So that leaves 1 minus 0.95, which is 0.05, or 5%, for the tails. But because of the symmetry, the two parts and the two tails are exactly the same. They're half of that 5%, so they're 2.5% each. So the alpha over 2 is the area right here in the far right, which is 0.025, and the same for the unshaded area over here to the left. Now, if we knew ahead of time the mean, which we don't, then we can compute these values here, this 105 and 97.1. We can compute those. How will we do that? I'll let you think about that a minute. Well, we know this probability here to the left here, and we know to the right here is the same thing, so we know 1 minus that is the probability up here. I think we can probably go ahead and figure this one out. Well, we can, because we know how to figure probabilities like that from a normal distribution. So notice that 1 minus alpha over 2 is 0.975. That's the probability below the upper end. It's the unshaded area on the far left and the red shaded area together. And the alpha over 2, 0.025, is the probability of each of the unshaded areas. That's not stated exactly correctly on the slide. I'll fix that. But it should say this first one is the unshaded area. Let's go back. I'll show you what it is. So the 0.95 is the red area. This is 0.025, so it's 0.975 to the left of this point. And remember, when we do an inverse norm, we have to give it the probability to the left. So we do 0.975 inverse norm will give us this 105. And then if we want this one here, the 97.1, that's going to be an inverse norm, and we need the probability to the left, which is just 0.025. So we figure those two numbers here using our calculator. Inverse norm of 0.975, mean was 101. Remember, this is for the sample means. So the mean of the standard deviation of the x bars is 2. So use 101 for mu for the mean and 2 for standard deviation, and we get 104.919928. Similarly, we do the inverse norm of 0.025, mean of 101, and standard deviation 2 to get our 97.08007203. So in other words, we can find those two values that round off to 97.1 and 105. Now, this is the width of the interval we're going to look for. So we're going to use this to find the margin of error. So the margin of error is the distance from the mean up to this top number and the mean down. So this whole interval is 2e, okay, in width. So what does that mean? Well, the whole length of the interval is this top number minus the bottom number. Here it is to the tenths. 104.9 minus 97.1. That's going to be, that difference is 2e. Divide by 2, we'll get e is 3.9 pounds. So we get the margin of error is 3.9. Now notice that there's a 95% probability that we take a sample of size 36 and compute the mean of the sample, that's x bar, it will be in this interval. In other words, it will be in the red portion of the graph. So in other words, we have a 1 minus alpha equals 95% probability that x is in this interval from mu minus e to mu plus e. This 97.1 is the mu minus e, and the 105 is the mu plus e. Now in the next slide, we're going to turn this around. We don't want to know, we don't know mu, we know x bar. So this is kind of saying like we knew mu and we're going to randomly pick an x bar, and x bar is the variable. That's not really the way it works out. Mu is a constant, it's unknown, but we find an x bar, which we do know. So we want to kind of turn this interval around. So we do a little algebra here. So remember we're starting with a 95% probability, that's 1 minus alpha, that x bar is in the interval from mu minus of e to mu plus e. Well, that means x bar is between mu minus e and mu plus e. So mu minus e is less than or equal to x bar, which is less than or equal to mu plus e. Now I just want to solve this where I put the mu in the middle and get the x bars on the outside. So I'm going to subtract mu from all three sides. So that cancels the mu out on the left, leaving minus e, cancels the mu out on the right, leaving e, but it puts an x bar minus mu in the middle. Now I'm going to get the x bar out of the middle by subtracting it. That turns the middle into minus mu. But that puts a minus x bar plus the minus e and a minus x bar plus the e over here. Next, I want the mu, not minus mu, in the middle, so I divide by -1 or multiply by -1. Either way, that turns it into mu. And so notice when I multiply this side by -1, it becomes positive x bar plus e. And on the right side here, it becomes positive x bar minus e. But remember, when you take an inequality and you multiply both sides, or in this case all three sides, by a negative, it reverses the inequality. So what were less thans now are greater thans. Now the next step, all I did is rewrote it in the increasing order. So the smallest value of these three is x bar minus e. Then you got the mu, and then you got the x bar plus e. So x bar minus e is less than or equal to mu, which is less than or equal to x bar plus e, which is saying mu is in the interval x bar minus e to x bar plus e. So another way to say this, and if I say it this way, I think hopefully it makes sense. It says x bar is within e of mu. It's either between mu minus e and mu plus e, exactly when mu is within e of x bar, between x bar minus e and x bar plus e. So if we're 95% sure that x bar is in the interval from mu minus e to mu plus e, we're also 95% sure that mu is in the interval from x bar minus e to x bar plus e. So this interval at the end, the x bar minus e, the x bar plus e, is our confidence interval. So notice that there's a 1 minus alpha, or 95% probability that x bar is from mu minus e to mu plus e. That is, that it's in this red area, and so we can get an interval of the same width for mu that goes from x bar minus e to x bar plus e. That has a width of 2e, which is the same as the width of this red interval. And this interval down here is our confidence interval. It's not the red one up here. Since we really don't know the value of mu, we use the fact that we get the same area and a similar shape by looking at a standard normal distribution where we find z-scores, hence the name z-distribution for a standard normal. So remember, it's a value, x value, or in this case an x bar value, minus mu over sigma. And of course, when you do mu minus mu over sigma, that's 0, so the mean is now 0. And then we have this here, which is, up here we have mu plus e, okay, and when we subtract the mu, then we just get e, and then divide by the sigma of the x bars here, and we get this 1.96. And then it turns out we just get the opposite value over here because this is symmetric about the mean of 0. And remember, we use z alpha over 2. The alpha over 2 means this area to the right is alpha over 2. And it turns out this one, because of the symmetry about 0, is just the opposite. So we're going to continue with this same example. I've talked long enough on this particular video, but we're going to come back and continue this same problem and use this to go through the steps of computing a confidence interval in our next video.